All right, in this video, I'm going to go over problem 3.31 on mastering. This video is dedicated to Luke. So this is an example of how sometimes even the physics teacher gets torched on a problem, because I went into this not expecting it to be carrying a switchblade in its back pocket, and this problem ended up being a little bit more troublesome than I thought it would. So I kind of started out like, okay, draw the diagram, okay, label the diagram, it's projectile motion, and I tried to go about it like it was just a simple projectile motion problem. And I got down here and I did all this stuff with the substitution, and what I figured out is when I substituted that into there, that everything canceled out and everything equaled zero. So that wasn't going to work. So then I reevaluated, and so now I'm going to take a different approach. Okay, so taking equations from the reference sheet, one of the troublesome things about kinematics, they do not give you the constant velocity equation separately. You have to realize that when the acceleration is 0, 1/2 at squared disappears from this equation, and it just leaves you with x equals xo plus vxot. And I like xf, xi, and vxi. And then you can also apply this equation to the y direction, so just replace all the x's with y's, and it'll work for the y direction as well. So that's where we're currently at over here on the whiteboard. Now, what I did before was I tried to apply this equation to the entire motion, and things kind of canceled out and everything was equal to zero, basically. So that was not giving me any useful information. So what I'm going to do is since this is a symmetrical jump, I'm going to solve for the amount of time to go up, and that will be half of the total time, again, because this is a symmetrical jump. Now, if you weren't convinced of that, you could solve for the time to go up and then solve for the time to go down, and you would see that it would be the same as just doubling the time to go up when you added them together. So that is what we're going to do, and I think we're going to have another twist in there as we go, but we'll start working through this and see. So doing half the jump, the mountain lion is going to end up at a vertical position of 3 meters, starting from 0 meters. And here's where the trick is going to come in. The time and the initial y velocity are both unknown to us, so we're going to have to deal with that in just a moment. And really, there's two ways we could deal with that, and I'll try to pick the easier of the two of those for us to deal with. So we could use either the first kinematics equation here or the third kinematics equation, and I think I'm going to go with the third one because I think it's going to be the most sensible or most direct for us to do that. So I'm going to come down here and just write that out. So vf squared equals v, and these are all y direction quantities. I'm just not writing a bunch of y's because that's just excessive. Minus 2a delta y. Okay. So this is not immediately obvious, I guess, but at the very top, the y velocity is 0. So since we're doing half the jump, we're going up. Final velocity is going to be at the very peak there, so that's 0. Vi is still unknown to us, minus 2a delta y. However, we do know some other things here, and that is very good. So algebraically, I'm going to go ahead and move vi squared over to the other side. It'll be negative, so it's negative 2a delta y. So the negatives will cancel out, or you can divide both sides by -1 and remove the negative, a delta y. Here's the deal. This is gravitational acceleration, and delta y is 3 meters. And then we're going to square root all of that. And I'll pause for All right, so if you are an astute observer, you might have noticed that I copied the equation incorrectly here. So that's supposed to be a plus sign, that's supposed to be a plus sign, that should be negative, that should be negative, and then those two negatives cancel out. That's positive, and then you can take the square root of a positive number. Good luck with taking the square root of a negative number. Anyways, that all comes out to give us that our Vy initial is 7.668, and I think that'll be enough significant figures that we don't lose a whole lot in calculation, or if I can in the calculator, I'm just going to keep that. Now, that means that I have something to plug in up here now. T plus 1/2 negative 9.8 t squared. Now, we're going to jump over to Desmos and solve for t real quick. All right, so here we go. Wait, I think I need to do that. -3 plus 7.6. Okay, is that a reasonable amount of time? Yeah, I think so. Okay, so our only solution, conveniently, I think, yeah, is looking like this 0.782. So I'm going to state over here, solve by graphing, and 0.782. Okay, now once I have that time, this is the whole crux of projectile motion, is then we're going to take that time and plug it into the other equation and do something productive with it. Because we need to know the speed of the melt line just before it takes off. Now, conceptualizing this whole problem, speed is the magnitude, here's a good place to make a note. Now, I think that we will realize that our mountain line takeoff is going to not be totally vertical or horizontal. So we need both the x and the y. I guess I'll call that an I, even though it states the same. Like it means the same thing. The x velocity doesn't change because there are no horizontal forces on projectile motion. Okay, so with that pointed out, we need to find those two and then do vector addition with Pythagorean theorem and add those two together to find the length of the velocity vector. So we are solving for the length of the velocity vector. That is the ultimate goal. So in order to do that, we need Vy, which we have, and we also are going to need Vxi, which we're going to solve for with this equation. And I almost forgot something important, because remember we just did the time up, so our actual time is going to be double that because we're doing the time of the whole jump. So I made myself a little note there, times 2, and hopefully I don't forget that in the next 15 seconds. So anyways, xf is 10, xi was 0, don't know Vx, and 2 times 0.782. Okay. And I think I still have that value. Oh no, that's, yeah, okay. So I'm going to take that. Hold on, I'll be right back. All right, so I found another boo-boo here. That's not a plus sign. There shouldn't be a plus sign there. That's just multiply. Okay, so anyways, we're solving for VXI, 10 divided by 1.564, and that gives us 6.39, which seems like probably a reasonable velocity for the mountain lion to be going. That's actually kind of low if you really get down to it. That's like 12 miles per hour, maybe a little more. Yeah. Okay. So hopefully that's right. 6.39. And then we're going to do some trig with all this fun stuff that we have discovered. All right, so what we know is that VXI is 6.39 meters per second, and Vy is 7.668 meters per second. And we need to solve for the magnitude of those two. So we're going to do Pythagorean theorem. A squared plus b squared equals c squared. So 6.39 squared plus 7.668 squared equals c square root everything. I'll be back. All right, so after doing the trig, I got 10 meters per second, give or take a couple hundredths there, 9.98. I feel like it was probably intended to be 10. Now, we also need to do a little bit more trigonometry stuff. So let's take that on to get part B. So part B was asking us for the launch angle. So let's go ahead and take care of the launch angle. So the trig function of interest I would pick out here would be tangent, because we know opposite and we know adjacent. So tan of theta equals 7.668 divided by 6.39. And then if we do inverse tangent of both sides, we will get our final solution here. And let's get that 7.668 divided by 6.39. And that is going to give us about 50 degrees. 50.19 or 50.2. I guess 50.2 would be the most reasonable representation. Okay, so going with that. So a little bit of trig came back, but those are, well, they should be our final answers. Oh my gosh, not only did I get it right, but I got like dead on what mastering said it was. Let's go.